Hello guys, this is 6.1 and we're starting a new chapter. This first section we are going to learn about antiderivatives, or another name for that is integrals. But they are quite a little bit different. Antiderivatives means the function, and the integral actually represents the operation. Right. So let's take a look at something very simple. X squared. And if we take the derivative, it's 2x, right? So here, in this case, we can say that 2x is the derivative of x squared. Okay. Right, 2x is the derivative of x squared. But if we do it the other way, right, if we look at that direction, and that will give you the antiderivative. Right, in that case, we can say that x squared is the antiderivative of 2x. So that's the relationship between antiderivatives and derivatives. Yeah. So if we say that, if we call this f of x, then this will be f prime of x, right? So here we can say that f prime is the derivative of f, and f is the antiderivative of f prime. Now, another way to say this is, I'm going to introduce a new function. Let's introduce some new notation. Let's say I have a function capital G, right? And what capital G is that if you take the derivative of G, you get lowercase g of x. Okay? So here we can say that the derivative of G is the derivative of capital G is lowercase g. All right, let me write it down. The derivative of G is lowercase g. That is, we can say that we can call G is an antiderivative of lowercase g. Okay, so capital G prime is equal to lowercase g, so the antiderivative of lowercase g is g. The antiderivative of lowercase g is capital G. Maybe that would make a little more sense. All right, next let's look at how to graph an antiderivative. Suppose capital F is an antiderivative of lowercase f. That is, if capital F prime of x is equal to lowercase f of x, right? So if f is positive on the interval, then f is increasing in that, and f is increasing. If lowercase f is negative, then capital F is decreasing. If lowercase f is 0, then capital F is constant. All right, so what we're saying here in the first part of these three statements, we are talking about derivatives. Right? If derivatives is positive, then the function is increasing. If the derivative is negative, then the function is decreasing. If the derivative is 0, then the function is constant, right? So this is just a different way of stating what we know already using the notation of antiderivatives. All right, so let's look at one example here. Example 2, figure 6.1 shows the derivative f prime of a function f. All right, so this graph, this blue line represents the graph of f prime, and the values of some areas, right? So we have 0 to 2, the area on the curve is 14, and then 2 to 5, it's 20, and then 5 to 6 is 12. If f of 0 is equal to 10, sketch a graph of the function f. Give the coordinates of the local maximum and local minimum. All right, so let's start with this. So we know that f prime is positive between 0 and 2, which is right here. So this is positive, meaning f is going to be increasing, right? F is increasing. Right? And between 2 and 5, it's negative, right? Because the line is the line between x equal to 2 and 5 is below the x-axis. That means this is going to be decreasing, right? F is going to be decreasing. Right? And last but not least, between 5 and 6, this is positive again. That means F is going to be increasing, right? So I want you guys to pay attention to these 2 points at 2 and 5, right? So the green point says that f prime of 2 is equal to 0 and f prime of 5 is equal to 0. And remember what this means. When the derivative of a function is equal to 0, that means they are the critical points, right? Meaning they are either a local maximum or local minimum, right? Let's look at f of 2, right? So x is 2 and 5, right? And then f prime. So f prime is 0 at 2 and 5, right? And to the left of 2, the graph is above the x-axis. That means f prime is positive, right? Positive. And then between 2 and 5, f prime is negative. And then after, to the right of 5, f prime is positive again, right? So remember, this is the first derivative test. We can use that to check whether we have a local max or local min, right? So if we think about the graph of f, it's increasing and then decreasing after 0, right? So here we have a local maximum, and then for 5, right, to the left of 5 is decreasing, and then after 5 it's going to increase again, right? So at 2 we actually have a local max, right? And at 5 we have a local min, right? Great. So by using the first derivative test, we were able to figure out where the local max and min occurs. But the next thing is we want to figure out what those values are, right? What are the function values at local max and local min, right? The only one point we have is this. We know f of 0 is equal to 10. Okay, so let's see if we can figure out what our local max value is. Right. So to do this, we're going to first write out the definite integral for our first area under the curve here between 0 and 2. Right. So let's call this part 1. The definite integral from 0 to 2 of f prime of x dx. By the fundamental theorem of calculus, we can say that this is equal to f of 2 minus f of 0. Okay. Now, just like earlier in the previous videos 5.5, f of 2 is the unknown, right? Which is what we are trying to find. Okay. And we know f of 0, right? F of 0 is equal to 10. And we also know the left-hand side, right? That definite integral represents the area under f prime from 0 to 2. And from the question, it tells us that it's 14. And since it's above the x-axis, it's actually positive 14, right? So what we have is 14 is equal to f of 2 minus 10. Right? And by adding 10 over, we are able to get f of 2 is equal to 24. All right, next. And 24, that's going to be our local max at 224. Right, so this is going to help us out when we are graphing the function f. All right, now let's look at the second part, which is we want to figure out what the local minimum is at, right? So we want to find out the value for the local minimum, which is when x is equal to 5, right? To do that, we're going to do the same thing, all right? We're going to take the integral from 2 to 5. Now, we're doing 2 to 5 because we actually know the area under the curve for x between 2 and 5, right? So f prime of x dx, which is equal to f of 5 minus f of 2. And again, the only unknown here is f of 5, right? We found f of 2 from part 1, which is 24. Okay? All right. Now let's look at the area for the definite integral. The area under the curve between 2 and 5 of f prime, which is 20. But notice that this area is actually under the x-axis, so that's going to be a negative 20 for the definite integral, right? Which is equal to f of 5 minus f of 2 is 24 from part 1. Okay, and let's go ahead and add the 24 to the left-hand side, and we have f of x is equal to, f of 5 is equal to 4. Okay, and that is our local min at x equal to 5. Okay. Now, last but not least, we also need probably one more point, which is the endpoint 6. When x equal to 6, we want to find the function value for x equal to 6, right? In order for us to complete the graph, right? Because that's the one of the endpoint, right? So we can do the same idea, going from 5 to 6, right? Which is a definite integral of f prime from 5 to 6. That's f of 6 minus f of 5. And again, the only unknown here is f of 6. So let's see. The definite integral represents the area under the curve between 5 and 6, which is 12, right? And it's above the x-axis, so it's positive. So 12 is equal to f of 6 minus f of 5 is 4, right? And add the 4 over, we get f of 6 is equal to 16. All right, so we have a lot of points ready. Let's write those out, x and y. Now, the first given to us in the question is that f of 0 is equal to 10, right? So when x is 0, I shouldn't use y, I should use f of x. Okay, so f of 0 is 10, right? That's given to us. And then from part 1, we found that f of 2 is equal to 24. F of 5 from part 2 is equal to 4. And the last one from part 3, f of 6 is equal to 16. All right, and let's go ahead and try to plot these 4 points together on the same plane. Right? Okay, here we go. So first we have 0, 10. Right? Let's say 5, 10, 15, 20, 25. All right, so 0, 10, that's here. And then 1, 2, 3, 4, 5, 6. 2, 24. So 2, 24, that's way up here. 5, 4, 5, 4. It's about here. And 6, 16. That's about here. All right, so let's connect them with a smooth curve. Let's see what we have. All right, something like this. All right, and then down there, like that, and then go up to this point right here. Okay, so this will be a really rough sketch of what we have for this question, right? Given the graph of f prime, this is how we can find the graph of f, right? So first, you want to find out any possible critical points by identifying the zeros of f prime, right? Determine whether they're local maximum or local minimum by analyzing the graph, whether it goes from positive to negative or negative to positive. And then once you have done that, you want to be able to find the values at those local maximum or local minimum by doing definite integrals and utilizing the area under the curve to help you find the value, in this case, local max and local min. Now, of course, you also want the values for the endpoint, so we know where this graph is going to go on one of the endpoints. Okay, so this is just a really rough sketch of the function f, right? In reality, it might not be that accurate, but it will have the form or the behavior of what we have here. Right? So I'm just going to label these points. Right? And again, we have our local max at x equal to 2 and 24, right? Local max, and the local min at here, 5, 4. Okay, and that's it. All right, next we're looking at concavity, which is f double prime, right? So here, if a capital F is an antiderivative of f, then f double prime is equal to f prime, right? So f double prime is equal to f prime. Right? Then we can determine the concavity of f from the properties of f prime. Right? So this is actually a little confusing, and let me draw a picture to help you out. Okay, so let's say we have the capital F, and then you take the derivative, right? And then you get f prime, and then you get f double prime, right? And here we're actually giving them a different name. F prime, we're also going to call that lowercase f. And when you take the derivative of f, right, you get f prime, right? So capital F double prime is the same as lowercase f prime, whereas capital F prime is equal to lowercase f. Right, so basically what we're looking at here in this blue box, right? Suppose f is an antiderivative, capital F is an antiderivative of lowercase f. If f prime is on a positive on an interval, then f is increasing, and capital F is concave up on that interval. Right? And if f prime is negative on that interval, then f is decreasing, and the graph of capital F is concave down on that interval. All right, so let's talk a little bit about what we're saying here. They are actually talking about whether this part is positive or negative, right? So in terms of f prime, right? In terms of f prime, f double prime, sorry, capital F double prime. If f double prime is positive, that means capital F is concave up, right? If capital F double prime is negative, then the graph is going to be concave down. However, if we look at it in terms of lowercase f, right, then f prime positive means lowercase f is increasing. Oops, is increasing. And if f lowercase f prime is negative, that means lowercase f is decreasing. Okay, so they are actually saying the same thing using a different notation, which can be a little confusing. But if you can follow this table that we have up here, and then trying to understand what this box is saying, then you will be fine, right? But basically what they're doing is they're using different notation to explain what the derivatives mean, right? Overall, first derivatives tell you the function is increasing or decreasing, and the second derivative tells you whether it's concave up or down. All right. And of course, the inflection point occurs when f double prime is at 0, capital F double prime is at 0. And then it also is the same thing as when the lowercase f changes from increasing to decreasing. Okay. So again, this is a little confusing because capital F double prime is the same thing as lowercase f prime, right? Because we defined capital F prime to be lowercase f. And it's just different way to elaborate what we're looking at in terms of graph with different notations. Okay. All right, and let's see. Yep, and that'll be all for 6.1. Again, in 6.1, we're looking at a lot of the things that are more abstract, a little more theoretical, but definitely take some time to understand what we're saying in this section. It's just we're talking about the same thing, but in a different point of view and with different notations. Okay, and that'll be all. Thank you guys very much, and have a good day.